Good afternoon and welcome. My name is Anna Rowinska and I'm your technical host today. Thank you all for joining us today for our webinar, Working with Machines, Risk Prevention and Safety with Cobots and Automation. If you're having troubles hearing, please click on the bottom left where you see the microphone. Click on the up arrow where you can select various auto controls. Although your microphone is not enabled, you can ask questions at any time through the Q&A icon. Please use the session chat to connect with other attendees and to share your thoughts about the presentation. We will invite our speaker, Dave, to respond to as many questions as we can during today's session. Our moderator today is Hussein Sinai, OHS Audit Manager and Safety Engineer at the Alliance. Welcome, Hussein.
Thank you to everyone joining in today. Before we begin, I would like to acknowledge that I'm speaking to you on the unceded territories of the Stolo people in the Coast Salish region of southwestern British Columbia. The Manufacturing Safety Alliance of BC is the not-for-profit health and safety association, serving manufacturers and food processors. Please call us to answer your health and safety questions to help keep your workers safe. We also invite you to visit our website for safety training, resources, or information on the Occupational Safety Standard of Excellence Core Certification for Manufacturing. We are excited to welcome Dave Smith, owner and the lead trainer from Cobot Safety here today, who will join me in discussing the risks associated with automated machinery and the use of industrial robots, and key consideration for people working in and around collaborative robots. Dave, welcome and thank you for joining us today.
Thanks, Hussein, and good morning to everybody. It's my pleasure to be able to talk to you today about some collaborative robot applications, and I'll get into that in just a second. Do you want me to start now, Hussein?
Yes, please go ahead.
Okay.
Thank you.
Okay, hopefully everybody can see my screen right now.
You're all set, Dave.
Okay, perfect. So again, good morning. I'm over on the eastern side of Ontario, or in Ontario, so it's afternoon for me, but good morning. Just a quick review of today's agenda. I'm going to give a brief introduction of myself and some of my credentials and my experience. Brief history of industrial robot standards, so CSA versus ISO. Also want to debunk the myth and talk about what is an actual cobot. We're going to look at 4 types of collaborative operations, and I'm going to give you a brief introduction to risk assessment, the requirements, and the mock exercises. Risk assessment is really critical for collaborative applications. It's really what all of them are based on. There's really no prescribed method as there is for some of the other types of industrial robots. And then we're going to have a question and answer period. Just a quick disclaimer, all this presentation material is illustrative only. Every collaborative application is going to require its own risk assessment. And I developed these materials by utilizing and interpreting excerpts from industry safety standards. You're going to want to purchase those if you're going to implement a collaborative application and read them in their entirety. And just check all relevant standards and regulations applicable to your robot application. Since I'm in Ontario, some of you might know, so maybe you don't. We have a regulation in Ontario that requires us to have a pre-start health and safety engineer, professional engineer license in the province of Ontario to review all of our applications, cobot and other robot applications. Just a brief history of myself. I started working in Honda, Canada, manufacturing in 1988. I started in production in the weld department. After a couple of years, I got a posting and went on to become the department safety specialist. And then I moved to assembly plant 2, where I was their department safety specialist. We have 3 plants there. And then I became the safety medical in the safety medical department, the corporate equipment and construction safety specialist for all of the 3 plants. So I spent probably the last 17 years doing risk assessments, writing our internal standards, and trying to obviously make things a little safer. Since I started in 1988, we had some serious trouble. We had a lot of stuff that was unguarded. Hopefully you're not in that condition now, but if you are, there's definitely a way out of it. That's the good part. And then after I retired at the beginning of the pandemic, I started my company called Cobot Safety, and I'm the owner and lead auditor and technical trainer for that. A little bit of my professional development. I'm a CRSP since '99, and I'm a registered functional safety technician. I am a health and safety professional. I don't pretend to be an engineer. I have a fairly good understanding of it. But if there's any questions I can't answer today, I can certainly get you the answer from other people that are on my committees. So we got involved in robotic safety. Probably I joined the CSA robot standard, industrial safety robot standard in 2000. And that was just after one of my colleagues and a good friend of mine lost 3 of their fingers to an industrial robot when they were inside the cell in full auto. So we used to do that quite often. We always thought we had to be really close to the machine until that person lost their fingers. And then we started to really look at it from a different perspective. I also was involved in safeguarding machinery, and I'm still involved with that. And I also lockout and other control methods. I've joined that since the inception in 2003. We first published. And I used to be the chair of ISO TC 299 for robotics and robotic devices for Canada at the Canadian Mirror Committee at ISO until I retired, and another person has taken that over. I will be the chair for the upcoming Z434 standard. And I've also been involved in machinery safety. So that's just a brief intro on me. Now what I'm going to actually do is probably turn my camera off while I do the presentation, just so I don't get distracted. There'll be some opportunities for questions that I'm going to add in here. We have some pause breaks. If there's any questions, one thing I'm interested in is, where people work and if they actually use cobots. I don't know exactly how many people are actually using collaborative robots right now, but if you type that into the chat, then that'll give us a good starting point to have some conversations. So the first thing we wanted to do is just a pre-line training baseline exercise, just to see how much you know about some of these items we're going to talk about today. So hopefully you can see those questions that are being posted right now by the facilitator. So the first one is, which CSA standard applies to industrial robot safety? And it's one of those. Okay, so it looks like we got a little bit of work to do, but we had 58% of the people that knew that. That's good. And which ISO standard applies to industrial robot safety? So the first one was which CSA standard. This is which ISO standard. Okay, again, so it is 10 to 18. Most of the people knew that, but again, this is just a pre-training baseline. So this is good. We're going to talk about that, and I'm going to give you some more information on that so you can understand where the standards came from and where they're going. Which industrial robot standard should you follow in Canada? That was good. It's a bit of a trick question, so I'll talk to you about that in a second. I'm going to share all the answers for these. And the last question, true or false, there is no such thing as a collaborative robot or cobot. Okay, that's good. This one, most people knew that was false. And we're hopefully at this first question period, we can talk about that and why you felt that before I even gave you that information. Okay, great. So here's the answers to those questions. So the CSA standard that applies to industrial robot standard in Canada for sure is the Z434. The ISO standard that applies is the 10218, ISO 10218. That's in two parts. We'll talk about that very briefly. And which industrial robot standard should you follow in Canada? Always the most current industry standard. And I'll talk to you a little bit about that as I show you the progression of the standards, because the ISO standard is what we're following now. So that's usually published ahead of the Canadian standard. So if you really wanted to follow the most current one, that would be the best practice. Legally, definitely you should probably follow as at 434. But if you're really trying to move ahead and stay with the standards, it's always best to follow the most current industry one. And there is no such thing as a collaborative robot. So we'll talk about that. Even though our committee did think that at first, I'll explain why that changed. So just a very brief history of industrial robot standards and my involvement. As I mentioned, my first conference was probably around 1998 after we had severed somebody's fingers with one of our old hydraulic robots. When there was about 300 people in a meeting in the States for the RAA standard, the R1506. And I asked a question in front of about 300 people if hydraulic robots would meet the standard. And immediately the moderator, who was the director of standards development and now has become a close colleague of mine, asked me right away if I was from Honda, because I didn't realize Honda was probably the only ones using our own hydraulic robots. And he informed me that they wouldn't meet the 99 standard, they didn't meet the 92 standard, and he didn't think they met the 86 standard. And hindsight, definitely agree with that, since we had so many potential incidents with them. So that's why we began our involvement and we started to get rid of all of our old robots. Just a very brief standards lesson here, or history. Originally, I didn't want to go back too far because we want to get into risk assessment and that stuff, but we took the R1506-99, that became the base document for CSA Z434-03 when we first published it. And then we took those documents to ISO and wanted to make an international standard. The one thing we learned when we went to ISO is because they have a machinery directive in Europe that dictates how they write their standards and what machines must meet for safety requirements, we had to break our standard into parts 1 and 2. So the CSA Z434-03 and the R1506 became parts 1 and 2 of ISO 10218. First published in 2006 and then again in 2011. And this is important why I talked about following the most current standard. We didn't revise the CSA standard from 2003 until 2014. So it would have been more prudent for people to follow the ISO 10218, 2006 before that, and 2011 when we published that. Now what's going to happen is we took those two parts and we put them back into Z434, but ISO can only speak to integrators and manufacturers and not in the same standard. So you'll see the first standard, part 1, is for manufacturers. The second one is for integration. Again, it all went back in the CSA, but we had to add user requirements as deviations because we speak to the users in our standard and ISO, they do not. Then as soon as we introduced collaborative robots in 2006, the concept of it, and when we started that, we didn't even really know on our committee, to be honest, other than some manufacturers. It was almost like writing science fiction. We didn't exactly understand what a collaborative robot application or a collaborative robot looked like. We spent most of our time writing standards to keep people away from the robots, and now the person is going to work with the robot. So after the documents, especially the part 2 was not issued until 2011. As soon as we issued those, we had a lot of questions about, what is a collaborative robot? How do we implement these applications? So we wrote a technical specification that we published in 2015 that we worked on for 2 or 3 years after we published in 2001. And again, the goal is just to provide more guidance on collaborative applications. And the requirements of this are going to be incorporated into the next version. And that's where I'm going to just quickly show you here. Hopefully, I put these in the handout so you can look at it if you're interested, but we'll skip over it pretty quickly. Basically, the 2 parts we had now, 2011, parts 1 and 2, they're going to be combined with ISO TC 15066. We also wrote a couple of technical reports that they only provide guidance, not requirements. So we basically took all of these documents and we put them into the next version of 10218 parts 1 and 2. Those two documents right now are at the FDIS, which is the final draft international standard. So we can't make any more technical requirements, the changes, and we're hoping those are going to be out in 2022. We have, of course, had issues with pandemic and virtual meetings like everybody else. Those two documents will come back to those two documents will be come back to the North America. The R1506, the American committee, is going to adopt them, as well as Canada. And again, in North America, we're going to work with the Americans to develop user requirements. They're going to add a part 3 to the standard, but in Canada, we're going to try to keep it all in one document, either as an informative annex or a normative annex, which means you have to follow it. So in Canada, we like to keep all of our documents and all of our parts in one document if we can, just for ease of use. Okay, if there's any questions, we can talk about those when it first comes up. So we talked about, is there any such thing as a collaborative robot or cobot? And many of you answered no, and you're actually right. So this is really interesting. As I mentioned, we didn't even really understand collaborative robots in 2003 or 4 when we started writing this, and we continued to learn. I think the manufacturers had lots of information, but as you can imagine, with the new technology, they weren't really sharing because we have several competitors on the committee. So we did define the collaborative robot in ISO 10218 Part 2, and we defined it as a robot designed for direct interaction with a human within a defined collaborative workspace. What we quickly realized after that is that that was not correct, because you can actually use any type of robot. If you notice the robot in this picture, it's actually a traditional, what you would call a traditional industrial robot. The one on this side is a power and force limit universal robot, but they're both can be used in a collaborative application. So what we decided, and we did have, this is actually a picture of one of our meetings in Florida, but we had several debates about that because we continue to call them cobots during the meetings. I think that ship has kind of sailed where the industry is calling them cobots, but really there is no such thing as a cobot. It's simply a type of industrial robot. The application is critical, not the robot. The term collaborative robot has been deleted in the next edition, so we don't talk about that in 2022. I did come up with a definition that we proposed as the Canadian delegation that never made it in, but most people agree that it is probably most apt to describe this. So it's really just an industrial robot with safety features that make it suitable for integration into a collaborative application. And again, that definition is mine. It wasn't accepted by the committee, but we talked about it in our meeting this week for the Z434, and most people agreed that it's an apt description. So again, it's not the robot, it's the application. There was some key points in TS 1506 when it came out. The robots utilized in a collaborative manner must comply with Part 1 and Part 2. So the robots themselves, the manufactured to Part 1, and then the integration has to meet Part 2. And this specification just was developed to supplement and enhance those requirements. It provides additional guidance with respect to collaborative operations. So there's 4 types we're going to talk about. And it also introduced threshold values for power and force limiting applications. So we're going to talk about that because that was one of the biggest things when we started talking about collaborative applications. Somebody said, okay, well, how hard can we hit somebody with a robot, or how much force? And then of course that would depend on the body part that you hit and all kinds of different things. So as soon as we introduced this, there was a lot of big companies, including Honda, that's why we're participating, and Mercedes and other companies around the world in automotive that really needed some additional guidance. So that's why we created this. The collaborative robot industrial design, the operational characteristics are obviously much different than those for than a traditional installation. The operators work closer to the robot. You can have intended or unexpected contact. Those are actually, they can be intended. So if it's a power and force limiting robot or a hand guided application, we're going to be right up close to the robot, even moving it around by hand. So obviously that contact is expected. And the risk reduction measures had to be determined in a risk assessment. Risk assessment is always important. I think anybody that understands safety nowadays understands that almost every standard, every workplace, every government regulatory authority always wants to see risk assessments, because there's a lot of value in doing them and doing them as early as possible. With a collaborative application, it's absolutely critical because, as I mentioned, there's no prescribed method to follow. Every application will kind of rise and fall on its own merits as according to the risk assessment. So there are 4 types of collaborative operation: power and force levering, speed and separation monitoring, hand guiding, and safety rated monitored stop. The 2 that are most prevalent are power and force limiting and speed and separation monitoring. We'll talk about those, all of these types. So the first one here is power and force limiting. I'll just show you a quick video of a polishing application. This is a universal robot. I'll show a few of these, but I have no ties to any robot manufacturer or anything. They happened to provide me with some videos and I was able to get some offline. So these are just illustrated only. But you can see that the person can work in close proximity to that robot. And we're going to show that in a risk assessment, and if that after we have a brief question break, and we'll talk about that a little bit more. So power and force limiting, physical contact can occur between the robot and the operator. And again, it can be intended or unintended. And there's two types of situations for contact that we talk about in the TS 15066. It's quasi-static, so is somebody going to be pinched or clamped, and it's transient contact. So it's more of dynamic contact where they can retract and recoil. We'll talk about that because the force limits are different. So again, contact can occur to intended situations, unintended contact caused by an operator, or an unintended contact due to a technical failure. So those are the things that we need to consider. The two types of contact, I talked about this, but quasi-static, and these are my own pictures, even though they're not the greatest, hopefully they show you. If I get clamped by that robot, or if that robot pushes me against something that's fixed, that's a quasi-static contact. And those contacts usually last longer than a transient contact, which is basically referred to as dynamic impact. And the body can recoil or retract if it's going, if there's a potential to avoid being pinched or crushed. And the pressure or force is exerted on the trapped part of the body for a shorter period of time. So that was why it's critical that we started to define these contact situations and actually provide some values for the forces that you can apply. The risk reduction measures to reduce the contact between the operator and robot. Basically, the key is to ensure the contact doesn't result in harm, because as we already said, it can be intended. So we have to identify all the conditions that could result in contact situations. The standards always ask you to look for things that are intended or reasonably foreseeable. So again, reasonable foreseeable, it's kind of a vague term, but basically anything that you could reasonably foresee going wrong. How would we protect the person if that happened? Evaluation of the risk of each contact situation. Design of the robot and collaborative workspace to minimize the contact situation. So this will go back to the design stage of our risk assessment. Again, that's really critical. And we have to apply the risk reduction measures to ensure the contact force don't exceed the limits in Annex A. And we'll talk about those when we get to that. So force gauges are how we measure the force. This is important to make sure that once you measure the force, you have to make sure that it meets the guidelines in our table. I'm going to talk about it a little bit later, but if I forget to talk about it, I want to talk about it now. Change management with all of the programmable safety systems. And this goes to any type of automation. When you're using safety PLCs now, and we used to mix machine and safety functions together in the same PLC, we had one of our operators get his head pinched between a jig and a lift. And luckily we were able to lift the jig up against the force in the air cylinders to save them. But that was a result of us mixing machine and safety functions in a standard PLC and having everybody, all our maintenance people and engineers have access to them. So we had a near miss. Somebody went to change some parameters and they created another condition which said bypass the light curtains when all these conditions are met and this person's in the way. So that's what happened. We almost killed a person. It becomes so critical when we start talking about collaborative applications. So if I'm going to set all these power and force limits, and I'm going to, in Ontario, I need a pre-start engineer to come in and validate that. After I validate it, I have to make sure that nobody changes it. So at Honda, we started what we called a safety device alteration procedure, where management would have to initiate a change to any programmable safety feature or device, or even hard guarding. And then 2 authorized people would have to make the changes, and they'd have to be approved by device because we had different types of safety PLCs. So anyways, we went pretty far with that, but that allowed us for change management, in particular with pre-start health and safety reviews as well. We didn't want to have to keep calling the engineer in. So after we validated it, we wanted to make sure, but just a very critical point, because all of the safeguarding now, a lot of it with programmable access limiting for robots and stuff is invisible. So if something happens or changes, the operator won't know until something goes wrong. This is just a quick example of a collaborative application that we did at the Toronto Auto Show. The interesting thing about this part is that we actually approved the application in our safety group, and I have a few members from Honda that were on the committees with me, so we all had an evaluation of it. We actually selected a couple of robots that were URs, but our engineering group found a deal on some other robots and bought those. And then when we came back from our ISO meetings, we realized that they had selected the wrong robots and they didn't have the right features to use in a collaborative operation or application. So we actually had to send them back. And we proved that out by showing our risk assessment to our senior management team, and then they agreed. So the kids could come right up here. They put the suction cups right onto the robot, and then the robot would go over and put them on the car in a whatever pattern the kids were selecting. This is just shows a quick video on some power and force limiting safeguarding devices. And again, I have no relationship to any of these people. I don't know how often you would use these. There's probably other ways to do this as well. But if you're going to have contact with an operator, you could use this air skin. So those devices go right onto the robot. That was on showing that on the additional axis where you can stop it on the transfer, but they also can be connected to the robot. We did bring this into Honda to try it out as you know, just to see how well it worked. We didn't actually have one in operation, but it reduced the contact forces from about 100 newtons down to 20. So it definitely works. It's all safety rated. There's an additional cost to it. But if you really need the robot to go faster where you can't meet the other contact forces, then there are different ways to do this. This is just showing the same one. That's going to come down, and basically the air skin is on the wrist of the robot just to make sure that if anybody's arm got caught under there, then again, it would limit it to the forces in our table. I'm going to go a little quick because I would just want to get through to the part on the risk assessments as well. So this is one of speed and separation monitoring. As I mentioned, power and force limit that I just showed and speed and separation monitoring are the two key ones.
Manufacturing applications that need the speed and strength of industrial robots also need the dexterity and versatility that only people can provide. The challenge with human-robot collaboration is how to effectively and efficiently safeguard these work cells. Ensuring robotic work cells are safe for human entry can require considering an exhaustive set of scenarios and integrating multiple 2D safety systems to cover all the places where a person could go. This adds time and complexity at every stage of the process. FreeMove from Veo Robotics is a new comprehensive 3D safeguarding solution that makes work cells with human-robot collaboration safer, easier to design and integrate, and more flexible than previously possible. The system includes custom 3D time-of-flight sensors that are positioned on the periphery of the work cell to capture rich image data of the entire space. The FreeMove engine uses this 3D data to identify the work cell, including the robot, workpiece, human, and occlusions. It then tracks and calculates all possible future states. And if a human is closer to the robot than the protective separation distance, FreeMove signals the robot to slow and stop. FreeMove will automatically determine when it's safe for the robot to restart. By monitoring the entire work cell in 3D, FreeMove ensures that the robot operates safely in any scenario while simplifying the design and risk assessment process. FreeMove's real-time understanding of the space enables dynamic computation of the extent of the robot hazard, which moves with the robot and workpiece. It's calculated for you, eliminating the need to create custom spreadsheets with complicated geometries. With FreeMove, last-minute changes to the work cell can be done quickly and efficiently. Perform a simple backgrounding step in FreeMove's configuration software, and FreeMove figures out the rest. To learn more about how FreeMove can help you simplify your work cell design and more effectively safeguard your applications, contact Veo Robotics.
Okay, again, as I mentioned, I'm not associated with anybody. That person is actually on my committee from Veo, so he provided me with some information. But this is a really interesting one because it shows you how this is basically a traditional robot that you can use, and the robot has features that make it suitable for integration into collaborative application because it has safety rated monitored stops. It has all the different types of features that it needs. The programmable access limiting with the dual, this is a FANUC robot with dual check safety on it. So anyways, that's why those robots can be used. And that's why we got rid of the term cobot, because really it's just the application. So again, the operator and robot, as you saw in the video, they can move in the collaborative space at the same time. the risk reduction is achieved by meeting the protective separation distance formula that we have in our standard. And this is a really, really slick application, even though these, I think when we first priced them at Honda, they were about 40,000 US. But depending on the size of your cell, you're also eliminating the need for your perimeter guarding, which is quite expensive by the time you buy it and have contractors install it, for us anyway. And you're also reducing the footprint of the cell, which is probably the biggest thing because space is always limited. And the other thing, again, it can be used with any type of robot as long as that robot meets part 1 of the standard and has all the safety features. This one is, I just wanted to show you quickly, and this is in the handout, you can take a look at it. This is our speed and separation monitoring picture. It relies on knowing where the people and the robots are, of course. This one, I really like how they do it. They measure it right from the end of the workpiece. And it basically using the protective separation distance, the person can wander anywhere, and the robots, because of those 3D high-speed cameras, can tell where the person is. There had been some iterations of this before. I think Pills had a safety eye, but it never really worked. This one, I don't talk too much in this presentation. I do have a 4-hour course where I go through this stuff in a little more depth, but this one is just showing the protective separation distance. I just kind of mentioned earlier as an anecdote that when we went through this part of the standard, and our scientists, we had scientists from ABB, KUKA Robotics, and a bunch of other ones, they went through this, and it was really painful to watch all these formulas develop, but in the end, we came up with something that was really good. And again, we've already talked about this, but you can use different limitations, or you have fewer limitations on your end effector design, and as well as your robot speed and payload, because some collaborative applications, especially power and force limited, when you're in the proximity of the robot, they're going to have to move very slow, else you're never going to meet the thresholds. This one allows them to go a little faster, and then as you get closer, it slows down to the point where it could stop in time. There are some different examples of technology to continuously detect the operator. This one's just using a programmable laser scanner. So if you see, this is just a little, whether it's sick ban or whatever type it is, it's just making sure that it detects this person. And as they come closer, the robot will slow down in speed. And again, with the protective separation distance formula, it'll make sure that the robot, no matter if the person speeds up, the robot slows down quicker, and vice versa. It'll stop the robot for sure. And again, it is the responsibility to make sure the integrator usually puts these in. And if you're doing your own integration like we did at Honda, then it's up to us. But really, they have to make sure that all of this technology is third-party certified. So TUV is an independent testing laboratory that tests all these devices, and they make sure they meet the requirements in ISO 13849 for functional safety. We'll go through these last two fairly quickly because we don't use them very often, but hand guiding, operator transmits motion and commands to the robot via hand guiding device. The guiding device has to be located close to the end effector. It has to include emergency stop and enabling device capabilities. And this picture, I don't see the e-stop, and I made sure I told people there could be issues with some of these. I tried to grab some hand guided applications off of there. He does have a 3-position enabling device. I'm not sure that the e-stop is readily available. And it doesn't apply to power and force limiting robot operations. So again, you can see this is a traditional bigger robot. A power and force limited robot, we can even hand guide or hand teach. This is not lead through teaching, but we can do that with a power and force limited robot. So hand guiding requirements don't apply to that. The only example that we saw of this was we went to the single thing plant in Mercedes, where they have about 40,000 workers, and they have, I don't know how many plants there. The one plant we went in, they were making the, I think it was the S-Class or whatever, Mercedes, but very, very, very intense operation. We saw them with a hand guiding robot, and it was basically a 500-kilogram robot with an operator sitting on it, and he had his hands on 2 enabling devices, and he was guiding the robot towards the front end module where you put the bumper on and all the and in the engine compartment. And we did not think that was what we were intending in our standard at all, because if anything happens with that robot, he's driving it right towards a person, and it's a large payload robot. So they took that out of operation after we did the tour with them. But this is really just meant for stuff like that. You should never see people sitting on a robot or hand guiding it that way. This just talks about the operator sequence. Once you go in there to the collaborative workspace, it has to issue a safety rated monitor stop. And then the operator can now enter it and take control of the robot. Anytime they release the guiding device, it initiates a protective stop. So a protective stop is just a stop that retains the program logic to facilitate a restart. So it is a safety function. And then once the operator exits collaborative workspace, the robot can resume automatic operation. These are just hand guiding considerations, and they are in your handouts. So just for sake of time, I'll go through them really quickly. But basically, again, the proximity of the robot, you have to ensure the process doesn't require the operator to put themselves in a potentially hazardous location. So under the robot arm or between the robot and the workpiece. This is, again, all determined in the risk assessment. And the earlier you do the risk assessment, the better off you're going to be. And again, the operator has to have an unobstructed view of the entire cell to make sure nobody else enters. And the intended motion of the robot has to be intuitive. So it can't surprise the operator. He has to know where it's going to go, and it has to be controllable from his guiding device, which is his enabling device. And that enabling device, for people who don't know, is 3-position. So if I squeeze it too tightly or I release it, it stops the equipment. There used to be a term called dead man switch for a 2-position switch. And there was actually a person in the US in the early days of robotics that actually gripped one of those, but still got squished between crushed between a bullard and the robot. So, and the coroner actually had to remove the enabling device from their hand. So that's where that's what started the premise for the 3-position enabling devices, and they've been around for quite some time now. The last one is safety rated monitor stop. And this one I'll really quickly go through because it really doesn't apply that much anymore. So it's not a collaborative function on its own, we determined. We used to have lots of cells at Honda where the robot would put the part into the jig, and we used to have to lock down the wrist or turn off the drive power. But with safety rated monitor stop, and again, the robot has to be capable of achieving that functional safety requirement for that. If it put the part down here, we used to have to, as I meant, put it in a jig or clamp it. Now the operator, if this robot presents it into this work area here, the person could go through the light curtains. We wouldn't have to shut the power off on the robot or lock the wrist because the position of the robot is safely monitored. So this is going to go away on its own as a type of collaborative operation in the next version. But for a safety speed and separation monitoring, it's going to, if you get too close to the robot, it has to issue a safety rated monitored stop and protective stop, which is a safety rated monitored stop. And the same thing would be for a power and force limited operation. So, and it's also part of hand guiding. As you mentioned, the robot has to stop when we go in and hand guide it. So that would be another area where we have safety rated monitor stop. This truth table just talks about the robot motion or stop function and the operator's proximity to it. It's all based on ISO 13855, which is positioning of safeguards with respect to the approach speeds of parts of the human body. And again, the robot can operate non-collaborative if there's no one in the space. Once they enter the space, the robot has to make sure that we provide a safety rated monitor stop, and the robot system motion can continue when the operator is exited. So that's basically, it can start automatically. This one is the table. So we had to create some values for how hard you could actually hit somebody. So our study, it's not perfect. It was conducted in Germany at the University of Mainz. It gives values, and they're based on pain thresholds, not the onset of injury. So we had this discussion quite frequently because it's very, very, the numbers, because they're just based on pain thresholds, are very conservative. So they're not very high, and there's been some concern about that, but that's the studies that we have for now. And again, the results were based on a single study because we didn't have anything else to go by, and it was only conducted on 100 healthy adult subjects. So that's really small sample size, but that's all we could use. Now, transient contact, I'll show you in the table. Basically, we just took the quasi-static contact values. That's what the test was based on, and we multiplied them by 2. That was based on a literature study. We say right in the documents that we acknowledge further studies are required, and they may result in changes to these values going forward as more studies and more information becomes available. But as you can imagine, a lot of the studies, it's all based on funding and different things like that kind of slowed us up, but at least we got something. So here's the actual test equipment that they were using. They broke the body parts down into regions and then specific body areas. And they just basically push people with a probe. And again, the probe itself is, you can kind of see it here. It's not sharp. It's basically a flat surface. So that's probably a best case scenario. So you obviously have to think about that when you're doing your risk assessments. That's why the shape of your robot, all of your clamps, everything else should, if you're going to use them in a power and force limiting application where contact's expected, then you have to make sure all the components of the robot can't create a hazard. It does provide some values here for the forehead, the temple, and all that, and those different sensitive regions, but we actually stay in the standard. The contact exposure to sensitive body regions shall be prevented whenever reasonably practicable. And again, reasonably practicable is probably, I always call those terms specifically vague. So we meant to keep them vague, but they provide you some guidance, but also a little bit of leeway. So it's very difficult to gauge whether somebody could be hit in the head or the face, because you never know what the person's going to do. But again, yeah, you use these values as a guideline and it'll help you to get to a safer application. Couple of things that have quickly changed, and then we're going to switch to some questions quickly. Safeguarded space, for anybody that knew the old definitions, we used to have the definition of safeguarded space was the area defined by the perimeter guards. Those could be hard guarding or light curtains or like anything else that's electronic sensitive protected device. But that wasn't going to help us for collaborative applications where there is no where there's no perimeter guards. So we changed the safeguarded space to the space where safeguards are active or where the perimeter safeguards provide protection. So this now also says if we have a power and force limited robot and all of the features are active, then we can say that's the safeguarding, and the safeguarding is active. And that's why the people can get closer to the robot. We used to have a manual high-speed attendant program verification. I like to include these because they're very important to me personally. We had a couple of very serious accidents in our Honda US sister plants with people getting squished by robots. One person was walking out of the cell. Two of them were teaching at high speed. As he walked between his robot base and the other robot operator didn't see him, swung the robot around in high speed, squished him up against the other robot base, and he had to get airlifted to Ohio State University Hospital. We changed right then. That was back in about 2003. We disabled T2, high-speed teaching, on all of our cells, so you couldn't do it from inside or have attendant program verification. Then we had another accident at one of our Alabama plants where somebody down there was teaching at high speed. And I knew that because our teachers had gone down to support them, and they were kind of surprised at how they did some of their things and the speeds they taught at. And then one of their operators he broke some ribs after and punctured a lung after he was struck by a robot. So going forward, we're changing that in the standard where high-speed teaching and program verification is only permitted from outside the safeguarded space in manual mode. So you can't go in and program your robot. You can't verify the speed inside the cell. There used to be a time years ago where the robot took a different path from slow program speed to actual speed. That doesn't happen anymore. The robots are a lot more reliable. So you can't do that. So whenever you're using perimeter guarding, all the teaching has to be done outside the safeguard space. Okay,
Thank you very much, Dave. I have a couple of questions quickly before moving on to the risk assessment. One common question is about robotic welder. Are we considering them as a cobot, collaborative robots, or not?
That all depends on the slide that I showed. There was a welding application. So that was a hand-guided welding application, but it all depends on the application. So we also have welding robots at Honda, MIG welding and I think TIG welding, that happen inside a safeguarded space where nobody's around them. So again, it all depends on the application. But the slide that I did show, and I'll just quickly go back to it here. Sorry. So this one right here, this is actually a welding operation here. So this one would be considered a collaborative operation or application only because the hand guiding device is right on the robot. But I could still have a robot, like I said, a MIG weld robot. We had several of them in our weld department at Honda. They were all inside a safeguarded space and none of them were collaborative applications.
Okay, perfect. Another question, it's about ISO TS 15066 is also called collaborative robots in that specification. If 15066 is included in ISO 10218, will that 10 will also be removed in the new revision?
Yes, and that's interesting. I'm glad somebody caught that. As you can see, that, as I mentioned, it was so difficult when we first started this because we really didn't know what a collaborative robot looked like. We had one video from the manufacturer's robot, the Robot Manufacturing Alliance in Europe, that showed us some ideas of taking guarding away and that type of thing. But definitely we missed the boat because we even titled our standard collaborative robots, but now we understand it's changed. So that title will be gone, and you won't see necessarily TS 15066. There will be no mention of that other than the requirements will be absorbed and into the document. The main part of TS 15066 that we're going to bring over is definitely the pain threshold, the onset of injury, or sorry, pain threshold table. So when they'll be in one of the annexes for our standard in the 2022 version.
2022. Perfect. And the last one before moving on, how do you consider unintended contact consequences in the risk assessment?
Sorry, can you say that again?
How do you consider unintended contact consequences in the risk assessment?
And that's very difficult, as you can imagine. I think it all, again, it's going to be based on whatever the application is. If I have an application that I have somebody going underneath the robot, then I have to probably consider whether or not that robot arm could fail and a bunch of different things like that. If I design my application to keep the person out of the way, if there wasn't, in the event of any failure, then I'm probably okay. It's again, we say that, and a lot of the things you say are kind of difficult to totally understand unless you're looking at the cell itself. So, and you're not going to understand everything that's unintended. I guess some of the unattended contacts, it depends on your workforce and how many people are around, how well they're trained. There's all kinds of different things to consider. So I apologize for not being able to give you a direct answer on that. But again, it's another thing that's specifically vague, where we had to put in a requirement because we wanted people to consider that. But without seeing the actual application, it's difficult to tell you what those could be.
Okay, thank you very much, Dave. All good for now.
Okay. Okay, so I'm going to continue on here. And I do apologize. We got a little behind. I did try to jam a lot of information into the first. I probably should have went a little quicker on the beginning here. But again, you'll have the slides. It's a risk assessment, all comes down to a task-based risk assessment. It's not a risk assessment program, so I won't go into that too much. But create your team, make sure you have all your stakeholders. We started this at Honda in 1998. We did it on a whiteboard. We had a lot of success because we did it very early in the process. So the earlier you do this at the design stage, the more likely you are to be able to actually implement all your safeguarding effectively. One of the things one of our operators asked us is whether or not we could bury all the cables on this new line. That was in about 1999, and we just got rid of all our hydraulic robots. We had lots of cables on the floor. People could trip over them. So that person asked that, and although we couldn't bury them, the engineer said, we could dig trenches. We could put forms in the concrete because we haven't imported it yet. Put the trenches in there and put the cables in there, and then we'll just put expandable metal covers over them, anti-slip covers, where we could take them off if we need to access them. That's just a good example that if we hadn't started that right at the beginning, it would have never happened. It would have been way too expensive. So if you get all the people, I'm a big proponent of collaboration between engineering and safety and all the additional stakeholders, maintenance, everybody that could be affected. You want to identify all the tasks. And again, you'll see some of these in your handouts, but all the different things, these are tasks related to robots and collaborative robots, but there's all kinds of different things. You want to talk about operator intervention, maintenance, even equipment cleaning. Then, as probably most of you know, the hierarchy of safeguarding, once all the hazards are identified, we want to start at the top of this matrix. We want to, use elimination of the hazard, substitution if we can. I remember we went from lead-based paint to water-based paint. That was an example of substitution. Elimination, we tried to go from a lead-based solder to a non-based lead solder for some of the repairs on our side panels. That actually didn't work. So what we did is we just eliminated that process altogether. And if we had a flaw on our side panel, we would just change it completely. The methodology that I use for risk assessment, it came out originally in 1999. It was in the IR 1506 standard, and then it's been updated over the years. So it's the TS 15306. I find this, I use it a lot for robots, but it can be used for anything. We also refer to it in the CSA Z432. We never tell people what methodologies to use, but it has to have certain parameters otherwise. And those are all the requirements from another document called ISO 12100. So this methodology, we added some additional categories for severity. We used to only have two categories. You either had a first aid or you had a fatality. Now we have moderate in the middle so that we can do a more reasonable evaluation of the risk. We have exposure, the same thing. We added another one. It used to be less than once per day or shift, more than once per day or shift. And then we talked about preventing it. So can you actually prevent exposure to the hazard, in which in a lot of cases we can. So that's our third choice. The other factor is avoidance. So we want to make sure that the person, if there is an incident, they could get out of the way. Some of you may have remembered this or know this, but 250 millimeters per second, that's the magic number. So 250 millimeters per second is considered slow speed, and people can get out of the way. So they have a higher, they're likely that they'll be able to get out of the way of that hazard. This goes into this table here, and I just want to show you this quickly because I do want to get into a couple of the collaborative application ones. But if we have a serious injury and we have low exposure, it doesn't matter if we're likely or not likely to get out of the way, we're going to actually have a high risk. Okay, so if the robot's moving, it doesn't even matter how fast it's moving. If I was teaching the robot, we always assume there's no safeguards initially, so the robot can kill me. I'm going in there, it's low frequency because I should only be teaching my robot, less than once per day or shift, unless I have a huge problem. And we don't do the risk assessment based on commissioning where we're teaching for 8 hours at a time. We do it on regular production, and we do have requirements for commissioning as well. And then likely, not likely gives you a high. The good thing that I like about this methodology is that if I have a risk level, it equates to a performance level required. So PLR is the performance level required. This all comes from ISO 13849 as well, and we've adopted into our standards. So anything that's high is going to be PLD structure category 3. Some of you maybe remember this as control reliable or dual channel with monitoring, but either way, it has to detect a single fault before the next demand on the safety system, so that it's a safe condition if we have anything go wrong. So almost all the robots that you're going to see, whether they're in our document or any other, they should all be PLD category 3 because they all pose a high risk when they're not safeguarded. ARTIS 1506 methodology or .306 gives you a methodology for how to evaluate the risk. When I retired from Honda, I had one of our engineers, a young guy there. I hired him to build me my own functional template that I use now. I just want to go over a quick. I've already showed you the video for this one. This was the policing application, and I just wanted to show you how we would put that into a risk assessment. So the first thing we're looking at, obviously, we have all these different tasks. For the purpose of this, we're only going to look at probably one of them, just because I'll have to go a little bit quicker here. So again, when you're doing a risk assessment, you have to assume that all of the there's no safety when you do the first one. That's the same as every risk assessment methodology. You always start out assuming that we have no safeguarding. So if I'm looking at the robot programmer, the hazard type is struck by the robot. We don't want them to have unintended contact between the operator and robot during programming, transient contact, and we don't want the operator pinched between the robot and the buffing table during the programming. That's quasi-static. If we go through and evaluate this before, you can see that we have a serious injury because we could definitely kill somebody with a robot, an industrial robot, if we don't have any safeguards. The exposure, again, because their programming is low, and the avoidance is not likely because the robot is still at high speed. So again, it's not likely, not possible. The other one, that's for explosion or eruption and stuff that you physically can't get out of the way of no matter what happens. But this one would be not likely. Still comes out to a high PLD structure category 3. Then when we put in our risk reduction measures, so now we have to put in all our risk reduction measures and we have to go back and look at this again. So if I'm going to utilize a robot that has power and force limiting capability, that's compliant with its standard, that's one of my things. As I mentioned, our Honda risk assessment for the collaborative application we did, when they didn't use a robot that complied with part 1, it's totally stopped us in a risk assessment because we were able to show, hey, that's the type of robot we need. So we actually had to incur a cost of sending back the wrong robots and buying some new ones. The good thing at Honda is we had a very strong safety culture, and once we showed our reasoning for it, it was a no-brainer, and we especially for an auto show where kids are going to be around, so we definitely change that. Ensure the teach pendant is active during programming if required. So the safety rated limited functions are not active, i.e. the safety rated limiting functions are not active and the risk is not reduced by inherently safe design. So if I have an inherently safe design in my robot, where I have all of my safety rated limiting functions like power and force that are already active, then I can do it. But normally they're not. So I want to ensure that all those are active. And if they're active, then I'm good to go. So I'm going to make sure that they have a teach pendant with a 3-position enabling device. We're going to make sure that all the teaching is done at slow speed. So we're not going to teach it at higher anything that's not avoidable. We're going to design the collaborative workspace to minimize unintended contact between their operator and the system. And we're going to clearly identify the collaborative workspace with floor markings. And again, keep in mind, this is just a sample risk assessment. But there's a lot of things to consider. One of the things that I should maybe mention really briefly is that a lot of people think that in a risk assessment, severity cannot be reduced no matter what you do. I have a lot of professional colleagues that are experts that I argue with all the time about that. I don't know that either one of us is wrong, but I definitely think safety can be reduced if there's, to me, the severity of the injury is all based on energy. So if I remove or control the energy to the robot can't hit me as hard, thus the severity is going to be lower. So, and in a collaborative application, if you don't change the severity, you'll just be in a continual loop and you would never come back out of that. The last thing I'll mention on this is just that you have to make sure when you do any risk assessment that you make sure that you complete the risk assessment. I first did audits of our risk assessment program after we started, and people would tell us, departments would report that their risk assessments are all complete. But when we checked deeper on our audits, we would find that not all of the responses, not all of the countermeasures were actually completed. So we put another system in to check for all that stuff. And I know I'm getting very close, so I'm just going to skip through a couple more slides here. These will be in your handouts, and I do apologize. As I mentioned, I took a 4-hour presentation down to 45 minutes, and I guess I kind of missed the timing a little bit. But you can take a look at some of these. I also show that for a speed and separation monitoring application, when the operator has to assemble them, and then all of the different things that you would need to do for that to reduce it to an acceptable level. And as I mentioned earlier, probably the most important thing is that when you do a risk assessment, you have to make sure that all of the controls you put in, especially programmable safety, that you have a strong change management system to make sure nobody changes those. Okay, sorry, Shane, I know that I kind of probably went a little bit longer there, but I don't know if we have time for the last knowledge confirmation or not. That's up to.
I would say, Dave, it's 10:58. We are going to have to stop here.
Okay.
Thank you very much, Dave. It's been a privilege to have you share your experience and knowledge today. A big thank you to our audience for joining us. We hope you can basically join us again to discuss mental health at work on March 17 in our town hall with the BC Minister of Mental Health and Addiction, WorkSafe BC Chief Mental Health Officer, and Canadian Mental Health Association of BC. Additional resources are available on our website, so make sure to visit our media library for on-demand content, news and resources, and event information. A big thank you again for joining us today. Please check your inbox for a survey link to share your feedback and suggestion and to help us improve future webinars. We will email you tomorrow with a link to the recorded webinar, slides, and the related resources. Thank you very much. Thanks again, Dave, and have a good day, everyone.
No problem. Thank you very much.